You write your Java code, run the compiler, and generate a .class file. At this stage, it's just a static stream of bytecode. But the moment you hit enter, that file is immediately pulled into a hidden, massive, and highly structured environment. The Java virtual machine is an abstract computing machine. It spawns an isolated universe inside your host operating system, providing its own memory management, execution threads, and security protocols to execute your logic. For backend engineers, understanding the mechanics of this universe is what makes it possible to optimize high-throughput systems and debug complex memory leaks. To see how it works, we can trace the exact journey of a single .class file as it moves through the runtime. The journey begins in the class loader subsystem, which is responsible for locating and fetching the data. From there, the bytecode is mapped into the runtime data areas, the JVM's internal memory model. Finally, the execution engine converts that mapped logic into host CPU instructions. These three pillars must operate in strict sequence for platform-independent code to successfully execute on native hardware. Before any logic can run, the JVM must fetch the .class files from the disk or the network. This fetch is governed by the delegation hierarchy algorithm. When requested, the bottom application class loader delegates upward through the platform loader to the very top. The Bootstrap class loader natively loads core libraries. If not found, the search cascades back down. The JVM follows a lazy loading strategy, meaning classes are only fetched when they are actively referenced by another part of the system. After loading comes the linking phase, starting with verification. A bytecode verifier checks the file to ensure it doesn't contain illegal or dangerous instructions. Then comes preparation. The JVM allocates memory for static variables, initializing them to default 0 values. In the resolution phase, abstract symbolic references are swapped for direct physical memory addresses. Finally, initialization runs the clinit method, which assigns your specific developer values to those static fields. This subsystem ensures that only verified, structurally sound blueprints are permitted to enter the runtime memory. Once verified, these blueprints are stored in the runtime data areas, which are divided between shared and per-thread zones. The thread shared zone is accessible by all operations and splits into two regions. The method area, or metaspace, stores class metadata. The heap is the primary home for every dynamically allocated object created by your application. Large memory references on 64-bit architectures can bloat this space, slowing garbage collection. To counter this, the JVM uses compressed ordinary object pointers. It fits a 35-bit pointer into 32 bits, allowing up to 32 gigabytes of heap with smaller, efficient references. Because this space is shared by all threads, it requires constant maintenance to prevent out-of-memory errors. This is the role of modern garbage collectors, like generational ZGC, which automatically identifies and removes unreachable objects in the background. Shared memory allows universal object access, but it relies on this combination of pointer compression and garbage collection to remain performant. While the heap is shared, the JVM is heavily multi-threaded and requires isolated execution paths to track individual tasks. Each thread gets a program counter register tracking its current instruction and a private Java stack. Calling a method pushes a new stack frame containing local variables onto this stack. These frames are instantly popped and destroyed when the method returns. If a thread interacts with native C or C++ code via the JNI, it branches out into a separate native method stack. By isolating the PC register and stacks, the JVM ensures each thread maintains its own internal state and control flow. While shared objects on the heap still require synchronization, these private zones prevent threads from corrupting each other's local logic and calculations. With the memory mapped and threads isolated, the execution engine begins converting bytecode into action. A standard interpreter translates bytecode line by line, which is fast to start, but creates a bottleneck during heavy execution. To solve this, modern JVMs use tiered compilation, which cycles between interpretation and just-in-time compilers across 5 levels. At level 0, the interpreter starts running the code immediately, while the JVM profiles the application to see which sections are running most often. The goal is to identify hot methods, functions dominating CPU time. At level 3, the C1 compiler takes over these hot methods, rapidly compiling them into native machine code with basic optimizations. Finally, at level 4, The C2 compiler applies aggressive global optimizations to the absolute most critical code paths. This tiered approach allows the JVM to achieve immediate startup times while eventually reaching the peak execution speed of native C++. When you view the runtime as a whole, you see an interconnected pipeline operating at massive scale. The class loader guarantees that only secure, verified blueprints enter the system. The runtime data areas strictly organize memory to balance universal object access with private thread execution. And the execution engine continuously optimizes the logic for the host hardware. This orchestrated environment is what allows the same Java bytecode to run reliably on everything from a handheld device to high-frequency trading servers, managing the transition from raw files to optimized machine code in milliseconds.